Now, first of all, let's start with the force itself in general. You see, we have this force, we define it to be dp by dt. For example, if you look at this thing cannot be the space component of a 4 vector. On one hand, P itself is the space component of a 4 vector. We had seen the energy momentum 4 vector. So dp is a space component of an energy momentum 4 vector, but dt is not a scalar. So that is why we cannot just say that we can generalize this f to a 4-dimensional vector with the space component given by dp by dt, because dp by dt is not the space component of any 4 vector. But you see, let's multiply and divide by gamma. Now that gamma dt, if you remember, it is nothing but d tau. Now here, dp by d tau is the space component of a 4 vector. Because p is a space component of a 4 vector, d tau is a scalar, it doesn't change from reference frame to reference frame. If you take a 4 vector, multiply it with a scalar, it is still a 4 vector. If you take the space component of a 4 vector, multiply it with a scalar, it is still the space component of another 4 vector. So we define this 4-dimensional force as dp by d tau. No, dp mu by d tau. And this p mu, 4 vector, we had defined it, if you remember, it's just m times eta mu. Now, if you write the components of this 4 vector k mu, k0 is dp0 by d tau, d by gamma, no, sorry. I think I made one mistake. 1 over gamma times 1 over gamma. 1 over gamma times dt is what we call d tau. Because d tau is just square root of 1 minus v squared over c squared times dt. Now d tau is dt over gamma of p0. Do you remember what p0 is? This is gamma times, it's just e over c. Well, the p mu, the momentum 4 vector, we had defined it as e over c and p. Of course, this is, no, yes, e over c. In energy. I don't put the vector sign. Let's look at the other components. Ki, this is dpi by dt, d tau, which is just gamma dpi by dt, gamma fi. So these are basically the components of K, 4 vector. Now, we know that if the let's go to the Lorentz force now. Well, if we calculate the components of the Lorentz force, we multiply it with gamma, we obtain the components of K. F was equal to Q times E plus V cross B. Let's look at the, let's say, the x component. The x component is q times the x component of the electric field plus v. Well, the x component will be the y component of v times bz minus the z component of v times by. Now let's write this in terms of the components of f above, f mu nu. This is equal to q times, well, Ex is nothing but c times f01 plus V2. Now Bz is f12 plus V3. Well, B minus By is f13. Well, let me write it slightly differently. This is q times minus c f01 plus v2 f12 plus v3 f13. No, sorry, not 0, 1, 1, 0. Why? Because I know that f mu nu is anti-symmetric, so if I change the places of these two indices, I get a minus sign. Well, let's add that term. I mean, you're right. I mean, one would expect a V1. It just looks quite symmetric with V2 and V3. Let's add the V1. If we had the V1 term, we would have V1 F11 plus V2 F12 plus V3 F13. This would look nicer, right? What is F11? F11 is 0. F mu nu is anti-symmetric. The diagonal entries are all 0. Look at the above matrix. You see, change the position of these two indices, you should get a minus sign. But changing the position of these two indices doesn't change anything. So F11 should be equal to minus F11. So it should be 0 all the time. But I would just add it. Write it here. Sorry, that is a typo. That is F10. This is F1, the x component of the force. So K1 you see, K1 is nothing but, look at the above, Ki is gamma times Fi. So K1 is just gamma times F1, which is Q times minus C gamma F10 plus Vi F1I. I'm summing over I. So K1 is equal to Q times minus, well, you see C gamma is nothing but eta 0 plus F1I eta I. So K1 is Q times f1 mu eta mu. Well, let me say nu. Well, sorry. Nu is a lower index. K1 is equal to Q times F10 eta 0 plus F1I eta I. Well, you can just calculate the K2, K3 just like that. I mean, it's not difficult to guess that K2 would be just F2 nu, K3 will be F3 nu. But these are nothing but this K1, K2, and K3. They are the space components of this 4 vector. K mu is equal to Q times F mu nu eta nu. And K mu is dp mu by d tau. This is the corresponding expression of the equation of motion for a particle in 4-dimensional notation.
K3 is QF3 mu.
Nu, yes. K1, K2, and K3 are the space components of this 4 vector. And in terms of this 4 vector, K mu, our equation of motion is this one.
Why didn't we count 0 as I? Why didn't we generalize I to 0?
Well, okay, first of all, we usually, just notation, we will have this Greek indices. Greek indices will always run from 0, 1, 2, 3. Therefore, general convention. You can still use Greek indices to run from 1 to 3, but it will be confusing. People are not used to that. Latin indices like I, J, K, they run from 1 to 3. Now, the second thing is, what is K0 in terms of the electric field? You see, we have this Lorentz force, which is a vector which only have the 3 components. So we are kind of trying to generalize the 3 components, this equation. The generalization of this equation to 4-dimensional notation is this one. This is the 4-dimensional generalization of that 3-dimensional equation. Of course, there is a question, what is the 0th component of this equation? Here, we don't have 3 components, we have 4 components. There's an additional component over here. What is that additional component? Now, let's look at the 0 component. dp0 by d tau is q times f0 nu eta nu. This is equal to q times f01 eta 1, f02 eta 2, f03 eta 3. Well, I didn't write the 0 component because f00 is 0. Well, this is equal to q times gamma, because eta i's, you see, they are nothing, f01 times u1 or v1 F02 times V2, F03 times V3. Now, F01, F02, F03 are nothing but Ex, Ey, Ez. Q times gamma E dot V. Well, the right-hand side, this side, on the other hand, you see P0 is E over C. This is gamma over C. E over C over here also. Gamma E over C dE by dt. This is dP0 by d tau. So I can cancel the gammas. I can cancel the C's. dE by dt is equal to Q times E dot V. Okay, just pay attention to the notation. There is no vector sign on top of this E. That is the energy of the particle. There is a vector sign on top of this E. That is the electric field. But this is nothing but the equation we already know. The rate of change of the energy of the particle depends only on the electric field. This is the power. If you like, you can write this also in this form. QE dot dl by dt. This is the electric part of the force. In a displacement dl, this will be how much work will be done. Well, in this expression, the magnetic field does not contribute because the magnetic field does not do any work. If you divide the work done per unit time, the work done per unit time is nothing but the power. Yes, I mean, this is the proof that the magnetic field does not do any work. It directly follows from that equation over here, the four-dimensional equation of motion. We see that the magnetic field does not change the energy. No, we never said that. We only said the magnetic field does not do any work. The electric field does do work. No problem. The work itself is a frame-dependent quantity. Energy is a frame-dependent quantity. The power is a frame-dependent quantity. You see, one typical example is the elevator. If you hold a book in the elevator and the elevator goes down, okay, for an outside observer, you are displacing the book in the direction that you are exerting the force, so you are doing some work. For you, inside the elevator, you are exerting a force, but the book is not displaced, so you don't do any work. So energy, work, power, etc., they are all frame-dependent quantities. If you go from one frame to the other frame, they should change. Sure. You see, K0 is the power. And K0 is the zero component of a 4 vector. It's not an invariant quantity. It's not a scalar quantity. It is the zero component of a 4 vector, and it changes from reference frame to reference frame in the way that any other zero component changes. And kind of that completes the book. We did. You see, what we looked at is we calculated K0 and we equated K0 to dP0 by d tau. K0 is E dot V with gamma and C. You see this equation over here. We started from this equation. This is K0, the zero component of this one. And we had shown that K0 is Q gamma over C E dot V. And this is equal to gamma over C dE by dt, which is the power. So K0 is power up to some proportionality constant. Now, an interesting exercise would be how to write the conservation laws in this four-component notation. Conservation laws. You remember we derived the conservation laws at the beginning of the semester. But now we will be dealing with four components. We won't be dealing with energy and momentum separately, but we will be deriving the conservation law for the energy momentum four vector. Anyway, I will not do it, but it will be a nice exercise, let's say. Well, you see, in terms of these four component notation, let's say P mu will be conserved. P mu is the energy momentum density. Being conserved, it means that if you take there should be some quantity. No, hold on, let's see. We already have the conservation of charge. And conservation of charge just tells me that del rho by del T plus the divergence of J should be equal to 0. This is the conservation of charge. Well, this tells me I can write this in this form. Derivative of rho C with respect to C tau plus the derivative of Ji with respect to Xi is equal to 0. This is derivative of J0 with respect to X0 with a lower index, so that is why I have this minus, I insert this minus sign over there, plus derivative of Ji with respect to Xi with lower index. Okay. So this should be equal to 0, but this I can write as derivative of J mu, this is, I would rather keep the upper indices, plus. This I can write as derivative with respect to x mu of J mu, this is equal to 0. So if I have such an equation, that tells me that the quantity which we define as J0 integrate over all space, which is nothing but the total charge multiplied by C, is conserved. Now, for the energy momentum, we should be able to find some T mu nu. We take its derivative with respect to x mu. This should be equal to 0. We should be able to derive such an equation, which will tell me that the integral of T 0 nu which I will identify is the new component of the energy momentum for vector, is conserved.
How can we say this is conserved by the integral?
Well, you see, if this is satisfied, what do you mean conserved? You just take that thing, take its derivative with respect to t, and you show that it is 0. This is equal to dp nu by dx0 multiplied by c. This is equal to c times derivative of t0